molecular elements before we talk about molecular compounds. Hopefully we'll get this all done today here. Many non-metal elements exist as molecules, aka there's more than one that are joined together. Things like iodine, I2, H2, N2, O2, F2, Cl2, Br2, etc., etc. I have no better clever friends, people stupid, P4, S8, yes? So molecular elements. In these elements, the atoms are sharing valence electrons. So there is no more give and take. We're just strictly talking about non-metals here. So there's no metal to lose electrons, and there is non-metals, but there's not that giving and losing or taking and receiving kind of thing. So they're just simply sharing electrons. Why do they share electrons? Because they want to become more stable. The only way they can do that is to share them, all right? And it's in order to fill their valence orbital. The sharing of electrons is known as a covalent bond. Make sure you know that. Covalent bond, sharing electrons, non-metals. That's what those all go together. These elements slash compounds eventually we'll look at are still neutral. There has been no loss, no gain of electrons. So there's no positive charge, there's no negative charge. They are still neutral. They're sharing, okay? So we're going to take a look at hydrogen here. Why does hydrogen come in twos? Well, hydrogen wants to, of course, fill its outside energy level. How many electrons does hydrogen need to have a full outside energy level? Take a look. How many does it need? Somebody, anyone, I don't care. Yes? No. Yeah, one more, right? So it's got one. It needs another one to become two, right? Become like helium. So to do that, it basically shares electrons. Well, here's one hydrogen. Looks like that. That's how we drew them before, Lewis diagram. Obviously, like I said, how is it going to get two around it? Well, you have to keep in mind that atoms, if we were to kind of blow them up, so if we made them bigger and bigger and bigger, and you picture an apartment building downtown New York, if you've ever been there, apartment, like apartment suite kind of thing, the electron, comparatively speaking, for that hydrogen atom, if it was an apartment in downtown New York, would be 16 blocks away. So it's not very close to the nucleus. It's actually quite far, relatively speaking. So if we shrink that down here, right, there's a hydrogen, here's another hydrogen here. You can picture that electron quite far away, okay? It's actually quite far away. So what happens is, as the electron goes around and around, another hydrogen's able to come close enough to it, and they're going to help each other out by sharing those electrons. So when these two come close enough together, okay, there's the electron going around and around there. Here's another hydrogen atom here with an electron going around and around. And there's some overlap there, okay, orbitals overlap. So what happens to those two electrons? Well, let's say there's one here and one here, but they are shared between those two hydrogens. So what actually happens? Well, sometimes the electron will go around and around like so, all right? Sometimes it'll actually go around both of these. So it'll go around here like this. And this one will go around, and it will also go around and around both of those. All right? So those two electrons are allowed to be shared between those two. To represent that sharing, we use what's called a line. All right? A line represents the covalent bond, the sharing of electrons. So usually what I like to do is I kind of like to get those kind of two electrons a little closer together here. All right? And we write it as that, the sharing of electrons, a covalent bond. All right? So we're going to put here covalent bond. Two electrons shared right there. Okay? That's what represents two electrons being shared. That's how we'll draw it. Okay? You have to keep in mind, these atoms are three-dimensional. They have electrons going around them. They flip over, they turn, etc., etc. We're trying to draw it two-dimensionally, and we're trying to draw it for a fraction of an instant of a second, okay, which is pretty tough. So we have to represent it somehow. That's how we represent it. All right? Good so far? Moving on. Oxygen. We know that oxygen has 6 valence electrons. So here's what oxygen looks like. 1, 2, 3, 4, 5, 6 is how I told you guys to draw that before. Lewis diagram / electron dot diagram, yes? Okay. Now, I know that oxygen comes in 2s. Why do I know that? Because I know the molecular elements. I've studied those. I have no very clever friends, people stupid. I know that oxygen is one of the ones that comes in 2s. So when you're walking down the street and you say, hey, look, it's oxygen, there's probably 2 of them linked together. Why? Well, look where oxygen is. How is it going to become more stable? Right? Think about the air around us. There's probably millions, well, there's probably a little bit more than a million. There's probably like babillions. That's a made-up number, by the way. Kajillions is also made up. There's kajillions of little oxygen atoms, right? And if 2 of them get close enough together, which is probably a good chance, if 2 of them get close enough together, right, they're going to share those electrons. So, once again, like I said, we're drawing 2-dimensional stuff. I'm going to do a mirror image just so it kind of lines up a little bit more. So I told you to draw oxygen like that. That's how I want you to draw it. But for simplicity's sake, or to get these kind of to match up here, I'm going to do the mirror image over here. Okay? Remember, these atoms, they flip around, they turn. Actually, these electrons are going around and around, but it's a little bit easier to see how they're going to match up here. Okay? When those 2 come close enough together, okay, how are they going to help each other out? They're going to start to pair up electrons. They're going to start to share electrons. How do we represent that? Well, these 2 here can kind of combine together. They can be shared between the 2 of them. And these 2 here, same thing, can be shared between the 2 of them. So actually, in this case here, we get what's known as a double covalent bond. 2 covalent bonds, okay? We represent that with 2 lines. The lines, of course, represent a pair of electrons that are being shared. Now, once again, all these electrons are being shared, so they're all going around and around, but those unpaired ones are allowed to hook up, make a bond between the 2 of them so that they're shared. Okay, that's how we represent it. I'm going to tell you right now, this is a little bit advanced, so we're going to get there. That's not really the best diagram of oxygen. The best one is where we try to kind of separate electrons, pairs, I guess we'll call it, well, that's what we're going to call them. The best diagram is when you can kind of get them as far apart as possible from each other. That's kind of back to that Vesper thing I talked about earlier, which we'll learn about, so just relax. If you draw that, it's fine. I'm going to tell you the best diagram looks something like this. In about lesson 9 or 8, we're going to get the molecular model kit, which is a fancy word for Lego. And we're going to play with it, and we're going to show you that that's kind of how that would look. All right? So we'll get there eventually. Double covalent bond, all those electrons are being shared between those 2 oxygens. Look, oh, sorry, I should have done one more thing here. Back up to here for a sec. Sorry, back here. Look, how does hydrogen have 2 electrons? Look, hydrogen's got 2 electrons, right? That one's got 2. That one's got 2. Those 2 are being shared between the 2 of them. Becomes a little bit more stable, okay? How does this one have 8 now? Well, once again, look, I'll do it up here on this one. 2, 4, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8, yes? Okay? Well, look, 8 there too, yes? Okay? So that's why you find, that's why O2, oxygen's O2, because they help each other out to have full outside shell, become more stable. Nitrogen. Nitrogen looks like this. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Yes? All right? So 5. When they come close enough together, they will share. And you'll quickly understand that anything that's unpaired, in other words, any electron by itself, is probably not a good thing. we need to kind of pair it up, or it needs to be made into a bond of some sort. In ionic compounds, it would be the gaining and losing thing. In molecular, you want to pair them up. You want to share them, if at all possible. So, which ones are going to hook up here? Well, for example, those two maybe hook up. There's two that could hook up. And those two could hook up. And you say, well, they're on either ends. Well, remember, these electrons are going round and round. They're unpaired. They don't have a partner, so they're looking for one, help each other out. Okay? So when we do that, you get, well, paired up, paired up, paired up, 1, 2, 3. That's obviously known as a triple covalent bond. Okay? And once again, that's technically not the best diagram. We tried to get electrons as far apart as possible. You might say, look at these three in the middle, though. Those aren't as far apart as possible. Well, actually, they kind of do turn out to be that. We'll show you when we get to the Lego, basically. Okay? We like to kind of spread stuff out, all right? Make it look symmetrical, if possible, all right? So that's what nitrogen would look like there, all right? Triple covalent bond. Good? Questions, anyone? All right. Fluorine, chlorine, bromine, and iodine. It says they all have 7 valence electrons. You're going to be like, look at bromine. Where's bromine? How many valence electrons does it have? Somebody's going to say it has 17, right? Because look, count over, right? 1, 2, 3, 4, 5, 6, 17. Well, no. Actually, that's grade 13 stuff, right? That's that suborbital thing that we're not going to talk about here. Trust me, they're all one short of becoming like the noble gases. So they're all going to have 7. It doesn't matter which one you use, fluorine, chlorine, bromine, iodine, you're going to write 7 around them. Okay? Likewise with oxygen, sulfur, selenium, tellurium, they're all going to have 6. They all have the same, they're all in the same group for a reason. Nitrogen, phosphorus, arsenic, all going to have 5 around them. They're all in the same group. Okay? So we're going to do fluorine here. Fluorine looks like this, 1, 2, 3, 4, 5, 6, 7. Okay? We're going to do the mirror image again here. 1, 2, 3. Oops. Nope. Sorry. That's fine. I can still salvage this. There. I just had to think about it for a sec. Once again, okay, just flipped over kind of thing. When these two get close enough together, right? Look, there's a pair here that can be shared right there. And is that going to help each other out get to that magical 8? Absolutely. So we get this. Okay? And once again, you can count them up if you want. There's 8 around each one. And you don't have to show me this part here. I'm just proving to you basically that each one has 8 now, sharing. Okay? All right. I guess I could go back. If you want me to do nitrogen here, I could do that one again as well too. But if you don't believe me, I guess we can. There's 6 in the middle and there's 2 on the side. So 6 and 2 is 8. All right. Phosphorus is a bit of a tricky one. It's a little bit unique. I probably will not ask you to do phosphorus, but I wanted to because I wanted to show you there is other possibilities. And if we're going to do all the other ones, I didn't want to leave out phosphorus and sulfur. They'll feel left out. We don't want that. So phosphorus comes in 4s. You know, it is kind of unique, right? Phosphorus has to come in 4s, and we know that phosphorus has 5 valence electrons. So we look something like this: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'm going to do the flipped over version on the bottom just so they match up a little bit better. So I'm going to do like 2 dots here and that. Okay? So kind of just the flipped over version. As always, when you see unpaired electrons, like electrons by themselves, which they're actually called unpaired electrons, you'll learn that later. When you see these unpaired electrons, you probably want to start hooking them together. Also, look, if it's P4, if I need 4 phosphoruses together, you got to hook them up so that they're together. Otherwise, right now we just have 4 atoms of phosphorus. They're not hooked up at all. So the first thing I'd probably want to do is come in here and go 1. Those 2 can get shared. I'm going to share these 2 here. And I'm going to share those 2 there. And we're going to draw molecular compounds and ionic ones as well. But, you know, the whole idea is that they have to have 8 around them. So you have to stop and say, well, does each phosphorus here have 8? Is the question. They have 7. A good indication is that if you see one dot by itself, that's probably not good, because that means you have an odd number, right? 8's an even number. So we need to do something to fix that. Well, first of all, you might say, I don't even see 7. How is he getting 7? Well, look, right there, for example, is what I'm looking at. That's everything around the phosphorus, right? So 2, 4 for the bonds, 5, 6 on top, 7 on the side. Well, that's no good. So how am I going to get the other ones? Well, once again, unpaired, you probably want to start hooking some extra stuff up. So I'd say, well, look, these two are unpaired here. Let's maybe hook these two up, and let's hook those two up. And we'll share those as well. Now, the person, I'm not sure who that is yet. I haven't decided. There's going to be somebody in here that's going to buck the system, and they're going to say, well, what if I share this one and this one instead? And I'll say, okay, that's fine too. I'll prove it to you later. Okay? So it's okay. There's somebody going to be trying to be different, and that's okay. Okay? So we're going to hook those two up, the ones I did in green there anyway. We're going to hook those up. We're going to get, once again here, let me just fill this part in here. Okay, so we had this before. We're going to hook up these two here. So that's going to be a double bond there. And we're going to hook up these two here. And that's going to be a double bond there. So in fact, as it says here, phosphorus has an alternating single and double bonds. Now, for those people that wanted to hook up, oopsies, those two, and then obviously the top two, well, then take this and turn it, and you get the same thing, okay? And that's quite often going to happen when we're doing these structures. There's probably more than one way, symmetrical. Yep.
Isn't it possible to cross the bonds through the middle?
No. Can't. You'll learn later. Patience. All right. S8, okay? S8. S starts with, sulfur starts with S, stop sign starts with S, 8, octagon. So, here we go. Once again, this one's a little bit trickier, so S. Now, you'll quickly understand later throughout the year that my artistic ability stopped in about grade 2, okay? So, just keep that in mind. Let's see, S, here we go. Well, this is going to turn out pretty good, I think. Oh yeah, there we go, stop sign, okay? When we did sulfur, when we did drawings of sulfur, I asked you guys to do this. 1, 2, 3, 4, 5, 6, right? Valence electrons, 6, sulfur looks like that. I really do want you to still do them like that. I'm not going to do them like that today. And I want you to do it like that for a reason. That will lend itself to the proper shapes that you're going to see later on. If I do that for every one of these, it's not going to match up all nice and pretty. My stop sign's not going to look very nice. That's what I'm trying to say. So I'm going to, you know, keep in mind these electrons go round and round, so it's probably okay. But that's better, okay, the way I've drawn it there. This is not the good way to draw it, because you're going to get confused and you're going to think structures are perhaps, once again, I know this maybe doesn't make sense. You're going to think they're linear, but they're probably not. Okay, so this is probably the only time you draw sulfur like this. So you're still going to have two that are kind of free, right? Two that are unpaired. And you're going to have, the other ones that are, of course, paired up here. Believe it or not, they're called paired and unpaired electrons. Pretty fancy term for those electrons there, okay? And S8, there's not really any too much thing about this. You're just going to basically hook them up here. So connection, connection, sharing those two. We're going to share those two. Oops, that's a single bond there. Share those two. Where is it there? Share those two. Shadows. Share, share. Okay? So once again, you're going to get that kind of structure. It's actually fairly large. It's one of the reasons it's a solid, et cetera, et cetera. We'll learn about that later. Okay. Once again, of course, if you look at this sulfur here, we're looking at all those electrons there, 8. Okay. So that's why sulfur hooks up like that. Okay. Good so far? Questions? All right. Remember, the whole idea here is that these are molecular elements. We're going to talk about these before compounds, which we're going to do right now, but they want to become more stable. The only way to do that is to share their electrons, right? So, next page. I think you guys have all the notes for this, so we're going to kind of breeze through this quickly. Molecular compounds made up of two different nonmetals. Same thing, they want to share electrons. We are only going to look at binary, in other words, two different atoms, that's it, okay? So like carbon and oxygens, hydrogens and oxygens, nitrogens and hydrogens, for example, in the same formula, binary 2, okay? So there's not going to be more than 2. One of the things about molecular compounds, first of all, there's no charges, we're sharing. They are, there's no reducing anything either. So like with an ionic compound, calcium 2 plus, O2 minus, we'd swap, drop, and reduce, CaO. We don't reduce here. So what we're saying is, you know, you can look here, C6H6, that's a 1-to-1 ratio for carbons to hydrogens. So is C2H2, but we don't reduce those down. We absolutely do not. Acetylene, okay, is very, very different than benzene, has very different properties. Those are very different compounds. That's why we have to use prefixes for molecular compounds to decide how many of each one we have. All right? To name molecular compounds, we're going to name the first element. If there's one, we don't include a prefix. If there's two or more, we have to use a prefix. The second element, always has a prefix, always, and also always ends in "ide." So here we go, next page. Here's the prefixes I promised you yesterday that you'll have to write in there, I think. And I'll move it up here. Name the following no, sorry, back up one. There we go. Unfortunately, I already have these names here for you. So, you know what, I'll let you copy them. We're on a time crunch here, so I'll let you copy them, then we'll talk about them real quick. Let's start here. So how do we name these, of course? Well, you look at the first one. There's only one carbon here, so I don't need a prefix. So carbon is carbon, of course. Always need a prefix for this one. One oxygen is mono, and then, of course, we have to change it from oxygen to oxide. So carbon monoxide. One carbon, no prefix. Two oxygens, so di. Oxygen becomes dioxide, of course. So always change the ending to "ide." Here we go. Two or more, I need a prefix. So dinitrogen, okay, di. Monoxide, one oxygen, okay, monoxide. Here, dinitrogen. I won't do it again. Dinitrogen, tetraoxide, 4 oxygens. Do not get, there's no swap and drop here. Okay, it is not more complicated than looking. Basically, there's a 2 here, for example. This is dinitrogen. There's only a 1 here, so that's monoxide. Don't try and flip stuff right. People want to switch stuff around. It's not that complicated. Okay. Next page. We're going to name a few more here. 2 sulfurs need a prefix, more than 1. So this is disulfur. 5 oxygens, so 5 is penta. Oxide. Okay. P3. Triphosphorus. You'll like it. Not everyone's writing stuff down. Triphosphorus. You'll like it. I'll say it again because not everyone laughed. Triphosphorus. You'll like it. Okay. 4. Tetra. Oxide. Okay. Triphosphorus tetraoxide. This one here, Once again, students like to kind of freak out here. They like to make up their own names. Is that a C and an L, or is that C and an I? We don't know. If it's C, I, and O, I don't know how to name that. That's too many elements. So it's got to be C and an L, yes? We're only going to do 2 elements. So this is chlorine, right? We don't need a prefix. First one, only one. And then, of course, 2 oxygens is dioxide. Okay? Chlorine dioxide. Nitrogen, no prefix, only one. Trihydride, you'll like it. Trihydride. Okay? Nitrogen trihydride, also very commonly, I want you to know this name. I'm never going to ask you to name it this way, but you should know that nitrogen trihydride, NH3, is also known as, very commonly, ammonia. Okay? So you should know that. If I talk about ammonia, hopefully eventually you'll know that that's NH3. Ammonia is a base. We'll talk about that quite extensively in Unit 3. Ammonia is very close to the one on your periodic table called ammonium. Okay, ammonium is NH4+. So we'll take a look at these 2 structures and I'll show you the difference between them. Okay, obviously ammonium is used in ionic compounds. Ammonia is a molecular compound. Okay, formulas for carbon disulfide. Carbon, so only one, disulfide, CS2. Okay, not CSI, different. I don't watch that show anymore. I don't even know what's going on anymore. I used to watch it like a long time ago. Trinitrogen, you'll like it. Hexachloride, hexa, so 6. Usually I'd let you guys try these, but tetraphosphorus, tetra's 4, heptafluoride, hepta's 7. Okay? And then tricarbon, I won't even do it this time because no one's laughing anymore. Octahydride. Octahydride, that's 8, octa, C3H8. Eventually you'll learn that that's called also known as propane. There's a song about that, right? You're going to get to your worksheet here. Once again, okay, it's pretty straightforward. You're going to tell me the formula or the name. You're going to tell me if it's ionic or molecular. You're not going to fill in the soluble or insoluble part yet. We'll do that. Don't worry. We got time. I didn't tell you anything about that. Don't fill that in, please. Just don't. Even if you think you know, just don't. It's less homework. It's fine. But once again, keys that, what's the difference, right? Ionic, what are you looking for? How are you going to know it's ionic? What's the first thing you notice? Yeah. It has a metal at the beginning. It has to be at the beginning, right? So you're going to have a metal and a non-metal. And if it's molecular, it's going to be non-metal, non-metal, yes? So that's one thing. Secondly, if you're looking at the names, what are you going to notice that's different? Molecular has prefixes, ionic does not, yes? Okay, so molecular has prefixes, ionic does not. Those are 2 ways you can quickly tell, all right? And you need to be able to obviously tell. They're very different, all right? We got sharing, which is not very strong, okay? Unfortunately, I wish it was stronger, but for a Catholic school anyway, it'd be nice. Sharing, not particularly strong. We got losing and giving, opposites attract, very strong. Okay, so just so you guys know.